Hello everyone, welcome back. My name is Alok Barik. I am from Department of Physics, Madanapalle Institute of Technology and Science, Dept University. So let us see where we have left in the last class, and we discuss today about some more interesting thing that is called Wheatstone bridge. Okay. Now suppose in this case there are 5 resistors or more than 5 also. We always we try to put the things in Wheatstone bridge form. So first let us understand what do you mean by Wheatstone bridge, what do you mean by balance condition in Wheatstone bridge, that is important, and how to solve such circuits which consist of 5, 6 number of resistors or capacitors. Okay. Now let us consider 5 resistors which is having resistance. Now let us consider this is the positive terminal of the battery which is having voltage V. So here also voltage will be V. Here 0. So here voltage will be 0. Here also voltage 0. Here voltage is V. Okay. Now this resistance is having suppose resistance R1. This is having resistance R2. This resistance is having resistance R3. This is R4, and this one is having resistance R5. Okay. Now this is actually Wheatstone bridge. Okay. Now in this case, if you see carefully, this is neither in series nor in parallel, so it is difficult to solve such a kind of circuits. So what Wheatstone bridge balance condition tells us that now when the ratio between the resistance R1 R2, when the ratio between the resistance R1 and R2 is equal to the ratio of R3 and R4, in such cases we can neglect this resistance. Why? Because why we neglect this resistance? Because no current will going to flow through these resistors R5. Or you can say that when this condition is satisfied, when this ratio is equal to this, then this point and this point are at same potential. The point, you can say that this point Z and this point is having also potential Z. So when this point and this point are having same potential, that is Z, the no current will flow, because when current will flow when there is a potential difference from higher potential to lower potential. In this case here, this is at higher potential, here this is at lower potential, so the current will flow. But when point, suppose let us name it, suppose this point is A, this point is B, this point is C, and this point is D. When point B and C are having same potential, that is Z, potential at B and C are suppose Z volt. Okay. In such cases, this condition will satisfy, and we can neglect this part, this resistor. We can neglect the resistor 5 because no current will flow from B to C. No current will flow from B to C, and these resistors will be meaningless. Okay. Now we can prove also this one, why these things will true. Now at this point, suppose if you see carefully, suppose current flowing through this is I. Okay. When it reaches the point A, the current is divided into I1 and I2. Here this is in series, so again the same amount of current will flow, I2. Here also at this node the same amount of current will flow, that is I2. Okay. So the total current, this I, is equal to, at this point, at this junction A, it is equal to I1 plus I2. Why? Because at the junction we have applied the Kirchhoff junction rule. So total current entering to the junction is equal to the sum total of current leaving through the junction. The same thing is true for this node also. Total current entering to the junction is what? This one will be I1. So total current entering to the junction is I1 plus I2, and total current leaving through the junction is I. Okay. Now if you see carefully here, what is the potential difference here? At A the potential is V, at B the potential is Z, at D the potential is 0, at C the potential is Z. Potential difference at this will be how much? V by V minus Z. So the current flowing through this circuit, a potential difference across this junction R1, this resistors R1 will be how much? V minus Z is equal to how much amount of current is flowing? Just apply the Ohm's law. This is the potential drop across the resistors R1. What is the potential drop? V minus Z. Why? Because V at higher potential, at A is at higher potential, B at lower potential. Then only the current can flow from A to B. So V minus Z is what? I1. I1 amount of current is flowing through this, and what is the resistance? R1. What is the resistance? R1. This is suppose equation 1. Similarly for this, if you see carefully this, what is the potential difference? Z minus 0. So this is equal to Z, because it is at higher potential, this is at lower potential, then only the current I1 will be flow, and which is equal to I1. And what is the resistance? R3. Okay. Now for this branch, if you see carefully, similarly V minus Z is equal to how much? I2 R2, equation 3 for example. And from here to here, the potential drop is Z minus 0, that is Z equal to I2 R4. Now if you divide equation 1 with equation 3, if you divide equation 1 with equation 3 and divide equation 2 with equation 4, then what will get? Z divided by Z is equal to I1 R3. Divide this with this and this with this. Okay. So I2 R4. So this will be how much? This equal to 1. So I1 I2 is equal to R3 4. Similarly here, if you divide these things, then V minus Z, V minus Z, this is equal to what? I1 R1 by I2 R4. So this will be I1 I2 is equal to R1 I2 by I1. Suppose I2 by I1 is equal to R1 by R4. So sorry, this one will be I2. Okay. So what we observe is that if you equate this and this, we can get that you can equate this and this, will get this one will be 2. If you equate equation, suppose this is 5 and 6, because in the left hand side I2 by I1 is there, so we can get that R1 divided by R2 is equal to R3 by R4. So when this equation is hold, question is that when this equation is hold, when the potential at B and C are same, in such cases we neglect the current passes through the resistors R5. Okay. Now if we solve one problem based on that, then we can understood what is the meaning of that. Suppose take a circuit. Okay, take a circuit for example, and suppose this is another circuit. Okay, and suppose here it is 5 ohm resistors, this is 4 ohm, this is 2 ohm, and this is suppose 2 ohm, and this is 1 ohm, and this is at some potential, for example 12 volt, and some current is flowing. Now question is asking, find out the equivalent, R equivalent. Okay, some current is flowing, suppose. Question is asking, find out the R equivalent of this. How to find out the equivalent resistance in this case? So if you see carefully, neither it is difficult. No, it is not in series, not in parallel also. Here we apply the condition for the Wheatstone-Bridge balance condition. Suppose this one is R1, this one is R2, this is R3, this is R4, this is R5. When Wheatstone-Bridge is in balance condition, what is that balance condition? R1, R2 is equal to R3, R4. If this condition is satisfied, if suppose this condition is satisfied, in that case we will simply neglect this one. And indeed in this case this condition is satisfied. Okay, 4 ohm, so let us this one, 4 ohm by 2 ohm, this is equal to 2 ohm by 1 ohm. So in this case this condition is satisfied already. So we apply the Wheatstone-Bridge condition, we neglect the what is the resistance, what is that resistor R5. So now if you see carefully, these two are in series, these two resistors are in parallel. So you can find out this. So you can find out like this, these two resistors are in series. So what is the formula for series resistance? 4 plus 2. So this is 6. This is like this, 6 ohm. What is this one? 2 ohm. Okay. So this is 12 volt and some amount of current is flowing. This is the equivalent circuit. If you see carefully again, what will these two are in parallel? When these two are in parallel, what should be the equivalent circuit? What is the equivalent resistance of this? 1 by R equivalent is equal to 1 by 6, because that is resistance R1, 1 by 6 plus 1 by 2. So you can find out what is the value of R equivalent in this case. So we need to analyze by looking at the circuits consist of resistance. Suppose we first need to analyze whether it is in series or not. If it is series, then apply the series. If it is parallel, then apply the parallel combination. And if it is neither in series not in parallel, try to reduce it to the Wheatstone-Bridge configuration such that we can neglect and some of the resistor when this condition is satisfied. So in the next class we will see when we consider the circuit consists of circuit element capacitor, what will happen when they are in series, they are in parallel. Next we will see what will happen to the inductor when we insert the inductor in the circuits, or next we will see the diode in the circuits. So thank you.